Welcome back. So, we will take a small look again at what we have done. So, we had considered an open system with those inlet and exit plugs, and now after we have simplified, and as I mentioned, there is no longer any need to look at those inlet and exit plugs. So, from now onwards we will draw a much more simpler diagram for an open system, and this is how I will draw it. So, this is now going to be a very simple diagram with one inlet and one exit. Of course, if there are more inlets and exits, we know exactly what to do. Second thing that I would like to point out is the small difference that exists in the expressions whenever we go from closed systems to open systems. For a closed system, we did not bother about the mass in the system, it was always constant. And if we took a time derivative, then for the closed system we could write as follows. This is because for the closed system the mass does not change, but for an open system we found out that the mass in the control volume, that is the open system, can change, and it can be expressed as follows. So, the rate of mass flowing in and the rate of mass flowing out, they dictate how the mass flow or the mass inside the control volume changes. So, of course, if more mass comes in than what is going out, the mass inside the system will start accumulating and it will start increasing, and if the exit mass flow rate is higher, then the mass inside the system will start diminishing. So, this was regarding the conservation of mass. I will just write down again, this is closed system and this is open system. So, we can take a look now at the first law. You remember that for a closed system we could write the first law as follows, and if we took a time derivative, that is we try to find out how the energy of a system changes with time, then all we had to do was differentiate. We would have gotten dE by dt. So, this is the rate of heat transfer and the rate of work transfer. This is what is represented by q dot and w dot here. But if we consider an open system, this is how we write our equation. This is closed. So, one notices that the left side, that is the energy of the control volume, can be expressed as q dot, which looks similar to what is seen in the expression for the closed system, but the work transfer we take only w dot s, whereas there are two other components of work transfer which are involved or which relate to the mass flowing in and out, and those are written separately here and which are denoted by these two terms Pi Vi and Pe Ve with their respective mass flow rates. Sorry, there should be an m dot I here. And we will notice that there is also the energy flowing in, which is represented by m dot I Ei. Similarly, there is an energy flowing out which is represented by m dot E. So, these two terms, the energy inflow and exit, is an extra term which comes in an open system analysis, just like the mass flow in and out came in the conservation of mass. These two terms will appear in the first law analysis. Apart from this, there is this additional work to put in the mass into the system and out of the system, which we consider separate from w dot s, and you would remember that we separated out E as u plus kinetic energy plus potential energy, and the u and Pi we added together and got H. So, these are things that one must notice, and you will realize that just looking at this we can now easily do our second law analysis. You have spent quite some time in looking at the second law for a closed system, and it becomes reasonably easy after we discuss how the first law is derived in an open system to figure out what should happen whenever we derive the second law for an open system, which is what we are going to take up next. Thank you.